Hi everyone. So today's video is going to be basically kind of warming up to some of the ideas that are going to show up in calculus. So hi everyone. So in today's video, we're going to be talking about one of the main ideas of Calculus 1. And so what you'll see happening in this class is basically we're going to talk about this idea, this kind of like big idea that's going to keep showing up in the class. We're going to talk about it today. And then the rest of the week, we're actually going to transition to some other topics. But then we'll come back to this idea that we're talking about today with a little bit more detail, probably like next week. So just kind of give you a heads up on how that's going to go. So the idea we're going to be talking about today is rate of change. So this is in section 2.1 in your book. So one of the main ideas of calculus, and especially it's one of the main ideas of calculus 1 in particular, is measuring the rate of change of a function. So what do I mean when I say the rate of change of a function? Well, we'll get into some specific examples in a little bit, but just kind of generally speaking, when we're talking about the rate of change of a function, we're talking about how much do the outputs of the function change as the inputs are changing. So how much does your function f of x, how much do the outputs either increase or decrease as x increases? That's kind of a general speaking way that you can talk about the rate of change. So let's look at a couple of concrete examples of functions. So I'm just going to sketch you a couple of functions here. So first one, let's say, looks something like this. So the example, the function that I just drew here, let's say that this is called f of x. This is an example of a function that has a positive rate of change because as x increases, so as you move from left to right, the outputs, the y values, are getting bigger. So this is an example of a function that has a positive rate of change. And something that you might remember from pre-calculus is that we also call those functions with positive rates of change are called increasing functions. And that's a word that's actually going to come up a lot in our class. Similarly, you can have a function that is going down from left to right. So let's say this one is called g of x. This function, we would say, has a negative rate of change. Because as you move from left to right, it's going down. The outputs are decreasing as x increases. So, maybe just to kind of give like a concrete example, like let's say that these are graphs that represent temperature as time goes on. So the one on the left would represent temperature that is increasing as time goes on. And so that's why we would say the rate of change of the temperature is positive. Whereas the one on the right, if this was a graph of how is the temperature changing as time goes on, well, the temperature is going down. So we would say that the temperature has a negative rate of change. Okay, so that's kind of the basics of what we're talking about when we're talking about rates of change. So I want to talk about a specific type of function for a moment. So we already know how to calculate exactly what the rate of change is for a specific type of function. So we already know how to find the rate of change if you have a function that is a linear function. So we already know how to find the rate of change of a linear function. So linear function meaning something like f of x is equal to mx plus b. So linear function might look something like, oops, still getting used, I have a new pen that I'm using on my tablet and I'm still getting used to it. So let's sketch a function here. So this would be, let's say, f of x is equal to, I didn't really draw this very well, but I want to say that it's at 2x plus 1. So when you have a linear function like the one that I just drew, the rate of change is just the slope. So in the case you have a linear function, it is the slope of the function. And so the thing that's special about linear functions is that they have the same rate of change for the whole function, right? If you look at this line that I just drew, it's never going to change its slope. It's always kind of going in the same direction. It always has the same rate of change. And that's really something that is only true for linear functions. So in the case of the one I just drew, the slope of it is 2 because it says 2x plus 1. So here, the rate of change always is 2. However, most functions, so let me just write below here, this is an example of a linear function. However, most functions are not linear, right? There's lots of different types of functions out there, and it's very easy to come up with an example of a function that's not linear. So I'm just going to draw a function where I'm not going to give you like an equation for it. It's just going to kind of be a squiggle. So let's say that we're looking at this function. And so let's just call this g of x. So this is a non-linear function, right? It's not a straight line. It has, sometimes it's going up, sometimes it's going down. So when you have a function that is non-linear, the rate of change is not always the same, right? Sometimes this function is going up, sometimes it's kind of flattening out, sometimes it's going down, sometimes it's steeper, sometimes it's less steep. So here, in this example, and for any function that's not linear, the rate of change is going to vary. And so we don't yet have a good way to figure out like how to find the rate of change of this function at various places. And that's actually like one of the main topics, or probably like the main topic of Calculus 1, is going to be coming up with a way that we can calculate the rate of change of any type of function at a particular point. So the main tool that we're going to use, at least for now, is we're going to kind of take advantage of the fact that we know how to find the rate of change of a linear function. We're going to take advantage of that by using lines to kind of measure the rate of change of nonlinear functions. So I want to look at an example of how that's going to work. Open a new page here. Okay, so again, I'm just going to draw a function. So actually, let me just write down first what I just said, which is that we can use lines to measure the rates of change of nonlinear functions. So I'm just going to draw, again, kind of like just a squiggle of a function. So let's say that this is our function. So let's call this function f. So not a linear function, it's doing different things, it's going up, it's going down, it's sometimes steeper, sometimes less steep. So there's two specific types of lines that we're going to be using to measure the rates of change of these of functions. So one type of line we're going to be using is something that's called a secant line. So I'm going to draw an example of one of those on here. And I meant to have a red pen, but I guess I don't. So let me get that in here now. Okay, so let's say that I'm just going to kind of pick two x values here. I'm going to call them a and b. So let's say that this first x value is a and the second x value is b. So if you choose two x values and go to the points that have those x values on your graph, and you connect them with a line, that's what's called a secant line. So this is called the secant line from x is equal to a to x is equal to b. And some people might just say from a to b. So this is something that you actually talked about in pre-calculus. So the slope of the secant line is going to tell you the average rate of change of your function between those two x values. So the slope of the secant line from x is equal to a to x is equal to b is going to be the average rate of change of your function from x is equal to a to x is equal to b. And so what do I mean when I say average rate of change? Well, it's basically like, what's the general trend, right? Like if you look at this function, it's, it's going up, it's going down, but if we look at kind of the general trend between a and b, it's slightly going up. So it's not giving us like a lot of detail, but it's just kind of telling us this general trend idea. Okay, so how do you actually find the slope of a secant line? Well, if you think about it, it's basically just finding the slope of a line, right? And so to find the slope of any line, you're always doing the change in your outputs over the change in your inputs. Or you might have learned it as like y2 minus y1 over x2 minus x1. So if our function is f of x, well, the outputs corresponding to a and b are going to be f of a and f of b, right? Those are going to be the y coordinates of these 2 points. So the slope is going to be f of b minus f of a over b minus a. That's going to tell you the, actually I don't have to write that because we just wrote it above, but that's going to tell you the slope of the secant line, which is the same thing as the average rate of change. Okay, so that gives us some information, but like I just said, it's not a whole lot of detail. So for example, let's say that you wanted to figure out what the slope was at one specific point. So I'm gonna, oh no, so we're gonna undo that. Yes, learning new things every day. So let's say that you wanted to figure out what the slope looks like at a specific point. So I'm gonna pick this. And notice that if you look at this point on the graph is actually kind of sloping downward at that point. So whereas the average rate of change from a to b would be positive, right? The slope of this red line that we drew is positive. If you look specifically at this one point, it's actually going to have a negative. The graph is kind of slightly going downward. And so we're going to use a different type of line to figure out what is the slope or what is the rate of change at that specific value. And that's going to be something called a tangent line. And so the tangent line is going to be a line that like just barely kind of touches the graph. It should, whatever the point is that you're drawing the tangent line at, you should have a line that kind of is just barely kind of tracing along the edge of the graph, kind of following the same shape as the graph. So we'll see more practice with this. I think it's one of those things that's kind of hard to explain. You just kind of have to practice it and get for a sense for yourself. And I think I didn't draw this the best, so I'm actually going to go in and do it a little better. I think that's probably a little better. So maybe just to give like a counterexample. So like, for example, like this would not be the tangent line, right? Because that's not really, it's kind of poking through the graph. We don't want it to go through the graph at C. We want it to just barely touch the graph at C. It might go through the graph later. So like this green line, if I were to extend it, it could go through the graph later, but it's not going to go through the graph at C. It's going to just touch the graph at C. So again, that's what's called the tangent line. So this is the tangent line at x is equal to C. So the tangent line tells you what is called the instantaneous rate of change. So whereas with the red line, with the tangent line, we're kind of measuring the kind of just like general trend. Now we're going to be talking about what is going on at that specific moment. So the slope of the tangent line at x is equal to c is the instantaneous rate of change. At that particular x value. So maybe just to give you an idea of like, what do we mean when we say instantaneous rate of change? Think about like you're driving a car, right? And if you're driving a car somewhere, your speed is going to vary throughout the trip, right? Sometimes you're going to be going faster, sometimes you're going to be going slower. So if you just look at, how far did you travel and how long did it take you, you can use that to figure out what your average speed was. So average speed would be like average rate of change. If you wanted to know exactly what speed you were going at one particular time, like you look at the speedometer, right, in your car and it's like, okay, you're going 52 miles per hour at that moment, that would be your instantaneous rate of change. So maybe over the course of the whole trip, your average rate of change was something more like 60 miles an hour. But that doesn't mean that at every single moment you're going 60 miles an hour. So that's what instantaneous rate of change has to do with. Let me just go in and underline this as well. And by the way, and so in the worksheet that you'll do to accompany today's activity, you're going to be looking at an example that has to do with actually like thinking about a real world example with this stuff. So thinking about the speed of a car is kind of a good example for this idea. Okay, so I want to look at an example with an actual function that isn't just a squiggle, a function where we can actually calculate some stuff. So open that up. So we're going to be looking at the function, this is f of x is equal to x squared. So friendly, familiar parabola. So the first thing I want to do is sketch the tangent line. We're going to do it at x is equal to 1. So first thing we're going to do is so if we go to our graph and we go to x is equal to 1 and we put a point here, so I'm just going to try to make a line that kind of feels like it barely touches the graph, something like that. I don't know, that's definitely not perfect, but it's the right general kind of trend here. So one thing that we can do is when you have drawn a tangent line, you can estimate what it looks like the slope is, right? So in this case, it kind of looks like if I look at this point here and, I honestly didn't draw this perfectly. It probably, and maybe let me just redo it because I know what the slope actually should be and I want to make it work out. So let me just draw this a little better. It should be more like this. So if you draw it perfectly, you should see that the slope of it is 2. But you wouldn't know that, like I happen to know that that's what the slope of the tangent line is. But when you're drawing a tangent line, you really only know one point that lies on the graph, right? Like you only know for sure that it goes through the point that you picked. So we only know that it goes to this point 1, 1. Any other point that we think it goes through, we're just kind of guessing based on how we draw it. But as we just saw, I just had one that looked perfectly fine and then I erased it that had a slightly different slope. So it's kind of hard to eyeball exactly what the slope is. So what we're going to do instead to figure out exactly what this slope of this tangent line is, rather than relying on estimation, we're going to use this trick where we're actually going to do, we're going to look at secant lines, and we're going to use secant lines to figure out what that slope of the tangent line is. So we're going to find the slope of the secant line from x is equal to 1 to x is equal to, and then we're going to do a few different secant lines, and we'll kind of see how we can use these different secant lines to come up with a guess of what the slope of the tangent line is. So let's start with from x is equal to 1 to x is equal to 2. So I'm going to go on the graph and I'm going to draw another point when x is equal to 2. So when x is equal to 2, y is equal to 4. So this is our secant line. So the nice thing about the secant line is now we actually have 2 points that lie on the graph, right? We have the original point x is equal to 1, but then we're using another point, and because that other point lies on the graph, we know its coordinates. So we can actually find the slope of this red line, and we won't be guessing. We won't be saying, oh, it kind of looks like maybe it goes to that point. We're literally using 2 points that we know lie on the graph. So how do you find the slope of this line? Well, in this case, you can actually just kind of look at the graph and find it, but I'm going to write it down because this is going to be the method we'll use on the other ones. So we're going to do f of 2 minus f of 1 over 2 minus 1, right? That's like the change in our y coordinates over the change in our x coordinates. And so f of 2 in this case is equal to 4. F of 1 is equal to 1. And then we have 2 minus 1. So that comes out to being 3 over 1, which is 3. And again, you could have figured that out by counting the boxes as well. Okay, so that is kind of close to what the slope of our tangent line is, right? If you kind of just look at it, it's not too far off. So I want you to pause maybe and think about like where could you bring in? So we have this second point here. I'm going to kind of highlight it. Where could you put that second point that would give you a secant line that has a slope that's closer to the slope that we're looking for? So think about that for a second. Where would you want to move that second point to make this red line have a slope that's closer to the slope of the green line? So we'd want to move it closer to 1, right? So if, for example, we did our secant line instead of from 1 to 2, from now 1 to 1.5, let's say. So I'm not going to draw it on this picture because it's going to get kind of cluttered, and I have on Desmos, I have something pulled up that will actually show this a lot more nicely than I think I could draw it. But just picture that now we're taking this big red point that I made kind of ridiculously huge. We're taking that point and we're now bringing it, instead of being at 2, it's going to be at 1.5. So now we're looking at a secant line that goes from 1 to 1.5. So if we were to find the slope of this one, so I forgot to do this ahead of time, so I'm pulling out my calculator right now to do this. So feel free to follow along and do it yourself. So it looks like we should get 1.25 on the top and then 0.5 on the bottom. So it comes out to be 2.5. So it's a little bit smaller than the slope of what we started with, right? Because, and if you think about it, again, I'm not going to draw it here, but just visualize what that line would look like. It would be a little bit less steep because the second point is a little less high up. So let's try now x is equal to 1.1. So we're going to bring that second point even closer to the first point. So if we were to draw a line from 1.1 to 1 instead, and find that slope. So let's see, 1.1 squared is 0.21, and then we're subtracting 1, so that's going to be, wait, that's not quite right. What did I do wrong here? Oh, never mind. Sorry, I confused myself. 0.21 is 1.1 squared minus 1. So that's our numerator. And then we're going to be dividing this time by 1.1 minus 1, so that's 0.1. And so if you divide this out, you should get 2.1. So again, notice the slope is a little bit smaller than the previous one. So let's do one more here. So let's bring this really, really close. We're going to bring the second point to just be almost the same as the point we started with. So now we have a tangent line. And again, I'll show you a better visual for this in a minute on Desmos. But now we have a tangent line where, a secant line where the 2 points we're using are like almost right next to each other. So it's almost the same as that green tangent line. So if we use these 2 points, and we calculate the slope, we're going to get, drum roll, 201 divided by now 0.01. And so this is going to equal now 2.01. And so this trend is going to continue. If we were to do 1.001, so bringing that second point even closer, then we would get a slope of 2.001. So what's happening is that as we bring the second point in the secant line closer to the first point, which is 1, the slope of the secant line gets closer and closer to 2. Right? That's what we're seeing happen with these numbers. We had 3, then we had 2.5, then we had 2.1, then we had 2.01, and that trend is going to continue. And so what that tells us is that we can basically kind of guess from this, and then later on, this is just true. If you see this kind of thing happening, you can from that conclude that the slope of the tangent line is 2. So meaning that the instantaneous rate of change of this function at x is equal to 1 is 2. So as promised, let me just show you a little bit of a better picture of this. And maybe it will look better if I do this. So let me get rid of a couple things here. So right now I just have basically the same picture we just had, right? We have a parabola, and I have the tangent line drawn at x is equal to 1. And so right now, the other thing I just pulled up is we have this dotted line, which is the secant line between 2 points. And so what I'm going to do is I set this up so that I can kind of drag the second point around. So if you look, see the kind of highlighted point is moving. So this is where we started. This is when we had the secant line from 1 to 2. Then we brought the second point into being 1.5. So when it's at 1.5, notice now that the slope of that red line is getting closer to the slope of the green line. And now I'm going to bring it into 1.1. And at this point, they almost look like they have the exact same slope. And then I'm not sure if this will handle it. Yeah, this can't handle bringing it into 1.01. But you can see the idea that as the closer we bring this second point in to the first point, the more and more the slope of this red line is looking like the slope of the green line. And then same thing from below. So we started with points that were above 1, but we also could have started with points that were below 1. So if we had started with like x is equal to 0 and then brought that point closer and closer in, we would see the same trend happening. So this is going to be the general method that you're going to use on problems like that. So let me just kind of write that down in general. To find the slope of the tangent line at, let's say, x is equal to a. Instead, what you're going to do is you're going to find the slope of the secant line from your original point, x is equal to a, the place where you're actually trying to find the tangent line, to x is equal to b. So b is now representing that second point. And what are you going to do? You're going to bring that number b closer and closer to that first number a. And what you want to look at is what's happening to that slope. So in the case that we just did, we saw that as you brought that second point closer to the first point, the slope got closer and closer to 2. But in different functions, it's going to happen differently. So like I said, there will be a worksheet for today where you're going to practice this same idea. So basically, you're going to be working with a slightly different function, but doing the same idea of taking the secant line between two different points and bringing the second point in closer and closer. All right, so that's it for today, and I will see you all next time.